You ever see one of those giant wind turbines slicing through the air and just wonder, how much power is it actually pulling from the sky? I mean, these things are incredible feats of engineering, but it turns out even they have their limits. So today we're going to dive into the physics of that limit because it tells a fascinating story about efficiency and one surprisingly stubborn number.
It feels like it should be simple, right? The wind is just there. It's a limitless resource. So why can't we build a perfect machine that captures 100% of its energy? Well, it turns out the answer is pretty counterintuitive. And spoiler alert, it has nothing to do with how good we are at building turbines.
You see, the barrier we keep bumping up against is a fundamental law of physics. This isn't some engineering problem we can solve with better materials or a smarter design. It's a rule of the universe we just have to work around. And this rule comes with a very, very specific number.
And this rule? It's got a name, Beats's Law. It was published way back in 1919 by a German physicist named Albert Beetz, and it basically sets the absolute, non-negotiable speed limit for how much power any turbine can possibly get from the wind. It doesn't matter what it's made of, steel, carbon fiber, or pure magic, this law applies. And here is that number, incredibly precise, 59.3%. That is the absolute ceiling. It's known as the Betz limit, and it's the theoretical peak efficiency for any wind turbine. But why? Why can't we get that other 40-something%?
Well, the logic is actually pretty simple when you think about it. Picture the wind like traffic on a highway. Now, to get 100% of the wind's energy, a turbine would have to stop the air completely, right? Make its speed drop to zero. But if the air stops, it basically creates a solid wall, a massive traffic jam that blocks any new, fast-moving wind from ever reaching the turbine. The whole system would just grind to a halt.
So to keep that energy flowing, you have to let some of the wind pass through. And what Betz figured out is that the perfect sweet spot, the point where you extract the most energy possible without causing that traffic jam, is exactly 59.3%. In the real world, our best utility-scale turbines get about 75 to 80% of that limit, which puts their actual real-world efficiency in the 45 to 50% range.
Okay, so that's the hard physical limit for a single turbine. But this whole idea of a limit doesn't just apply to physics. It scales up in a massive way when you try to power an entire country and hit a goal like net zero emissions.
The physical limits of one turbine are one thing. But when you start talking about national energy grids and huge climate targets, you run into a completely different but just as real kind of limit.
And to really dig into this, we're going to look at a major 2023 report from University College London. They modeled a bunch of different scenarios for how England could get to net zero, and what they found reveals this critical trade-off that goes way beyond Betz's law. Because once you start planning renewable energy on a national scale, you realize pretty quick that the most precious resource isn't technology or even money, it's land. I mean, where are we going to put all this stuff? All the solar panels, wind farms, and energy crops?
And this brings us to a conflict that's kind of hiding in plain sight. The UCL report analyzed the land requirements for different renewables, and, well, one of them turned out to be a surprising land hog.
Okay, so take a look at this. To hit those net zero goals, the report's scenarios show that solar farms and onshore wind need a pretty similar amount of land, around 1,700 square kilometers each. But then, just look at that third bar. That's for energy crops, which is a type of biomass. In some of the scenarios, getting to net zero could mean we'd have to grow these energy crops on nearly 11,000 square kilometers of the English countryside. I mean, just let that number sink in. That is a staggering amount of land.
To put that into perspective for you, we are talking about a scenario where up to 9%, nearly a tenth, of England's entire land area would be dedicated to growing crops not for food, but for fuel.
And this is where you see this huge efficiency trade-off. The report points out that solar panels produce about 10 times more energy per square kilometer than biomass crops do. Plus, while you can sometimes have things like sheep grazing under solar panels, energy crops often compete directly with land we need for growing food.
So this massive demand for rural land, it forces a really important question. Are we even looking in the right place? The UCL report actually digs into an alternative solution, and it's one that's literally right above our heads.
So here's the choice we face. Do we keep dedicating huge swaths of the countryside to become energy farms? Or can we get smarter about using the spaces we've already built? You know, our cities and towns. Think about all the rooftops, parking lots, and industrial buildings.
And that's exactly what the UCL researchers did.
They did a deep dive to calculate the total technical potential for generating solar power, but just within England's existing urban footprint.
And the results? They are a real game changer. The scenarios estimated that, at most, England needs about 83 gigawatts of solar capacity to reach net zero. Now get this, the total potential the researchers found just in urban areas alone was 117 gigawatts.
Let me just say that again, because it's a huge deal. Theoretically, England could hit its net zero solar targets without building a single new large-scale solar farm out in the country. All the solar capacity they need could be found right on the buildings and developed land we already have.
So ultimately what this all shows us is that the path to net zero is this incredible puzzle of both physics and space. On one hand, we're constrained by these fundamental laws, like the Betz limit. But on the other, we're also constrained by the very real amount of land we have on our crowded planet.
And that leaves us with a really critical question. As we engineer our green future, it's not just about what technology we build, but where we choose to put it. The physics are fixed, sure, but the choices about our landscape, well, those are still very much up to us.